Professor.
What do you have there?
To ancient sailors, this piece of stone was more valuable than diamonds. In fact, anyone who tampered with one of these or who stole it would be tortured and put to death.
Over a stone?
Yes, a stone. A lodestone. Today on Science Fundamentals, we're going to find out why this lodestone was so valuable when we talk about magnetism. When we talked about gravity, we explored the unseen force that pulls everything towards the center of the Earth. Another unseen force, which occurs naturally, is magnetism. A magnet is surrounded by an invisible force field called its magnetic field. Now, this magnetic field affects certain types of materials and attracts them. Now, let's do a demonstration that will allow us to view the magnetic field. Okay, now each one of you take one of these magnets that I have here. Now, this is a bar magnet for you, Junior. And here's a horseshoe or a U-shaped magnet. You hold on to that, will you, Michael? And we have one more magnet here. We have a round magnet or a disc magnet I'm going to give to you, Jennifer. Now, I also have some iron filings right here. And we're going to put some of this in a cup. Each one of you are going to get some of these. These are just shavings from a larger piece of iron. And as we all know, iron is one of the materials that's attracted to a magnet. There we go. Some for you. Now what I want you to do is I'm going to give you a piece of paper. I'll give you a sheet of paper, which I've got right here. Let's get one for each of you. There's one for you. One for you, Jennifer. Michael. Here you go. Now what I want you to do, lift up your piece of paper in the air first and put your magnet on the lab table. Okay, just lay it down anywhere and put your piece of paper over the magnet. So the magnet's in the center of the paper. Now take each one of you take your cup and just like sprinkle little bits of iron filings across the top of the paper and see what happens. Okay, what's happened here? What do you see? Junior, what do you got there?
Nice, look like a bar.
Yeah, it looks like the shape of the bar, the magnet underneath it, right? They're all in line, okay? Now, what do you have, Jennifer? What do you have here?
Mine's a round shape, just like my magnet.
Exactly, just like your magnet. And over here in Michael's, he's got a horseshoe shaped where it's attracting just at the very ends of the poles. Remember, kids, have an adult supervise any scientific experiments you try at home, okay? Now, what you're seeing are the force fields around the magnets. Because the iron filings are attracted to the magnetic field, more of them will congregate where the field is the strongest. Now, on the bar magnet, the filings are on either end. On the round magnet, the force field looks fairly even all the way around. And on the horseshoe magnet, you could see how he had it on his over here with Michael. Okay, now, and in reality, a horseshoe magnet is just a bar magnet that's bent, right? Right. Okay. All magnets have a pole, a north and a south pole, okay? It's really clear on a bar magnet which is which. Let's do another simple activity, again with the iron filings, to show the way the poles will attract and repel material and each other. Now we're going to take a bar magnet like this. The north pole is marked in blue and the south pole is in red. And we'll take two of them and we're going to put them with red to the red and the blue to the blue. Put these back in the cup. Now we're going to take these papers and we're going to put it right like this. Now let's get some more iron filings. I think I have some saved up here, sure enough. Right here. Now Jennifer, you go ahead and sprinkle them over the top and let's see what finds. Let's find out what happens. So what happened, Jennifer?
The iron filings form lines that bend away from each other.
Exactly. The iron filings bend away from the poles of the magnet, showing the repelling lines of the magnetic force. Now, let's do the experiment again, only this time, put the opposite ends of the magnets towards each other, red to blue, blue to red. Let's see what happens then. Now, Junior, can you reach over here and sprinkle these over that? Just just like I did before. See what happened with this one? All the filings stayed in between the bar magnets, didn't they? They still form the same patterns, but you can see how they bend in a lot more in the center. The filings form lines that connect the two poles, showing the attracting lines of the magnetic force. This is because of their polarity, or poles. Now, the Earth has its magnetic field surrounding it. This is caused by the iron core at the center of the Earth. Compasses and magnets react to this field. Every magnet has a pole labeled north or south to correspond with the Earth's magnetic poles. Like poles repel each other. Opposite poles attract. Now, can all materials be attracted to magnets? What do you think, Junior?
No, not every material.
No, indeed not. Now, here we have some various kinds of materials. We have a plastic cup. We've got an aluminum can. We have, let's take a paper clip. Put that up here. We got some nails. These are some wire brads. Get some of those out. We got some sewing needles. Wow, that's a big one. Okay, now let's try our magnets and see what we can pick up with them. Give it a try. What do you got? It works on the spoon, on the metal spoon. It doesn't seem to work on that plastic spoon too good. What do you got over here, Michael?
It doesn't work on the ping pong ball.
No, and it doesn't work on that plastic cup. What about that aluminum can? It's got metal in it. No? No can do? Well, it seems like aluminum won't work. What's this? That's some kind of old washer. Try that one, Jen. Or Michael. There you go. That washer's probably got some iron in it, huh? Try that paper clip, Michael. Can you reach over and try that? Yeah, that worked pretty good. Paper clip's got it. What about those nails? Hey, they work pretty good. So out of all these items, the ones that were attracted to the magnets were the ones that had the most iron in them. And so what do we conclude from this? Jennifer?
That magnets only attract metal.
All metal? Michael?
No, it didn't work on the aluminum can.
No, it didn't work on that. What about the other materials? Junior?
Magnets didn't trap in plastic, like the spoon and the ping pong ball.
Right. Plastic, paper, stuff like that, the magnets won't attract. Magnets work on some metals, like iron and nickel and cobalt. So it would be a good assumption that if a magnet sticks to a material, it has some of these metals in it. Now, we can make these metals that are attracted to magnets magnetic as well. I'll show you what I mean. All right, let's take this beaker, and Jennifer, why don't you put some of those paper clips in? Get yourself a little handful. Okay, that's good. And I've got a nail here. Take this nail and reach in there and see if you can pick out a paper clip with just the nail. What's happening? They're not sticking, are they? No. Okay, now, Michael, what I'd like for you to do is I'd like for you to take this bar magnet and put this nail on the end and reach in there and pick out a paper clip. There you go. Just pull up one. That's it. Pull it on up. Good. Now hold the nail with one hand and pull the magnet away, and what happens?
It falls off.
It falls off. Okay, what happened, Michael?
The magnetism was only going through the nail, but the nail is not a magnet.
Right, exactly. Right now we're going to temporarily make the nail a magnet in its own right. A magnet is made of very small magnets called dipole particles that are all lined up in the same direction. Now, if I stroke the nail with the bar magnet in one direction only, it will cause the magnetic dipoles in the steel to line up, which should temporarily make it magnetic. Let's find out. Okay, let's do another experiment with this needle. Remember, the needle has to be made of steel, which has iron in it to be magnetic. A plastic needle won't work. I've suspended a needle on two pieces of thread and gently lowered it onto the water's surface. Now, very, very carefully, take the thread out from underneath the needle so it continues to float. Now, without touching the needle, move the magnet over the bowl. Yes, the surface of the water acts like a thin skin. This imaginary skin is due to the attraction of water molecules to each other. The needle is able to float and move across the surface of the water in response to the magnetic force of the attraction by the magnet. I wonder how many paper clips you can pick up with that.
I bet you have a demonstration.
As a matter of fact, I do. Tape your magnet to the edge of the table so it hangs over the edge. In fact, let's tape this small bar magnet, this medium magnet, and this large magnet. Bend open one paper clip for each magnet and touch one to the end of each magnet. Now, each of you begin adding a paper clip one at a time. Keep count of how many clips you can tag on before they all let loose and fall. Well, Michael, what happened with your magnet?
I had the most paper clips.
You had the most paper clips? Who had the next most?
Me.
Jennifer, you did? How many did you have?
I got 4.
You got 4, and you had the round magnet. How about you, Junior? What was your luck?
Just 2.
Just 2. Well, what happened?
I guess my magnet was weak.
Your magnet was weak. Its magnetic field wasn't strong enough to hold that many. It wasn't nearly as strong as the bar magnet that Michael had. We already learned about dipoles, that a magnet can affect the magnetic dipoles in steel or iron. These dipoles are also called magnetic domains. Holding the paper clips near a magnet causes the magnetic domains inside to line up. The strength of the magnet increases as the number of domains pointing in the same direction increases. Weak magnets have weak magnetic fields around them, so their effect on magnetic materials is small. The number of paper clips your magnet was able to support depend on its magnetic strength.
So, Professor, what about this old rock here? Why is it so important?
All right, let's go back to our iron filings. Let's place the tip of the rock in it and see what happens.
They stick, but why would someone kill someone over a magnetic rock?
Think about it. One instrument that uses magnets is important to navigation. Here's a hint. It has a north and a south pole.
A compass?
Exactly, a compass. A compass works on the magnetic principles we've just explored. It'll point to the Earth's magnetic north pole. So this was the first compass, and it was usually hung on a string or placed on a floating piece of wood in a bowl. And it was extremely important to sailors in the Middle Ages to assist them in their exploration and, more importantly, to finding their way back home. So today we've talked about magnets and magnetism. It's every part of our everyday lives. For example, magnetic material is what's used to coat audio and video tapes. It also helps transmit sound. There are magnets in the speakers in your stereo at home, the speakers in your car, or in your computer. So we can see they do a lot more than just hang notes on a refrigerator. Try to see what other magnets you can find around your house and try some of these experiments in your home. But be sure to get an adult to help you out. And remember, science is fundamental. See you next time.